This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Where it's supposed to, so I've still got a minute before I'll start flicking through slides. All we're going to do today, well, not all we're going to do. Today we're going to run through the subject outline so that we can understand what we're going to cover, where the assessment is, what does the subject look like, and we're going to have a bit of a chat about your own expectations of the subject, and then talk through what it is, what it isn't, why you'd study it, and what kind of science we're actually looking at here. It turned on. So now it's real. Welcome to thermodynamics. Welcome to thermo and fluids. And I can say it now for the record. My name's Rob Gordon. So I'm an academic here at University of Melbourne, and I've been here since April 2014. I've worn a lot of different hats over my career. This is now absolutely an academic life. I've previously been everything, so I did an undergrad in mechanical engineering and in commerce. After that, I was a management consultant for a while, and then in dot-com startups around the 2000, went into finance, and then when all of that all went on its head, I've done some travel, I've learned some languages, seen a few things around the world, and then later on came back to engineering to do my PhD, which is effectively your apprenticeship to becoming an academic. That was my undergrad and PhD were up at the University of Sydney. And after that, I then followed a fairly normal academic life of going into a postdoc, which is where you just do pure research, a research fellowship after that. And then I spent a few years in industry. I've been working for Rolls-Royce in their Montreal office in Canada, which is where I was running their research and development division for gas turbines. And so as a company, they do mostly gas turbines, not cars. And in the Canada office, they were doing industrial gas turbines, which are the GTs, the gas turbines that make electricity. So that's really where I got hooked into all things energy, and that's another of the things that I do at the University of Melbourne is I teach and run a degree called the Master of Energy Systems, which is not so much an engineering degree as part engineering, part finance, part policy, part law, all the things you'd need to know if you wanted to be working in the energy industry. So that's the quick background. Now, one of the things that doesn't often get told as an academic life, and I know you may not be terribly interested in me, but sometimes it's nice to know who the person is who's talking to you, is every single one of us here has a different life. So you see us as your teachers, as your lecturers. By definition, all of us are researchers. We view that as our first life, and then we teach. You see us, our first life as teachers, and then we go off and do something mysterious when you're not watching us. So my other life here is a combustion researcher, and I'm an experimentalist. And what that means is I'm trying to understand the physics and chemistry of fire, particularly as it's used in an engine, so a car engine or a gas turbine engine. And you do that to try to optimize either the efficiency of the engine or allow it to use alternative fuels, renewable fuels, change its pollutants, minimize greenhouse gas emissions. The science in this is hard, which is nice because it keeps me in a job. If it wasn't, it'd be fixed. And it's fun, mainly because my lab is shooting lasers at fire. And so once I realized I could get paid for that, I think I found the career for me. The reason I tell you all of that is because the topic I'm about to teach you is a core part of my life. So when I walk out of here, I'm using thermodynamics as the tool to analyze all the stuff that I'm thinking about. And so I enjoy teaching it because it's the first window into a world that I care very strongly about. The other reason why I like teaching this subject is there's a lot of introductory engineering subjects where you're kind of patted on the head and told to wait a couple of years before you'll get to the useful stuff. Particularly in the early maths, the early physics, you know you're doing it to build up some skills, but you know you're not walking out of the semester with something that you could use in a business place as a professional engineer. The thing I like about the intro thermo subject is the stuff we're going to learn in the next 6 weeks is useful. The first few weeks may not feel useful because we're going to spend a bit of time just clearly defining the tools we're going to use. But by the end, we're going to be learning a couple of equations, a couple of concepts in some depth that actually work. They are the tools you use to make things better. So we'll do a little course outline. That's enough for me chatting about me and my world and why I care about teaching you guys this stuff. The course outline, all the information about how to contact me, all the information about how to contact Joe is in the LMS. In fact, pretty much everything's in the LMS, which you probably know by now. If you haven't been in there, have a look around. My office is hard to find. It's hidden in a mezzanine behind a security door, etc. So if you're coming to track me down, let me know, because also I'm not always in my office. I know a lot of people have consultation hours. I float around between a lab, a couple of different cafes to get work done, and I'm bouncing all over the place on the university. If you want to come see me, send me an email. The absolute easiest way to track me down is to send me an email and I'll arrange to be around. I'm very happy to provide support. In fact, and particularly because I care about whether or not you're learning the concepts. The other thing is, however, some people feel the need to save up a lot of problems to make it worth coming in to see me. If you get stuck on something, send me a photo of your scribbles in the email. Send me the page of what you're stuck on. Quite often, I can solve your problem within 5 minutes of looking at the email and just bounce back to you. You've missed a term here. That was a minus. It should have been a plus. No, this concept only applies under this situation. So I don't mind you sending me stuff. Now, there's a flip side to that. I'm a human being. And so I may not respond to you immediately. Now, this may come as a shock sometimes. Particularly sometime after Friday afternoon and sometime before Monday morning. I'm also a father, and I've got 2 young kids, and this is a chapter in your life that just utterly dominates your disposable time. Everything you thought you had available to do things in suddenly gets all used up. And so I'll set aside little windows of time to get through my work. So I do get your emails, I do get your questions. If you haven't heard from me for a little while, I don't mind if you send a reminder after a day or so saying, did you get that email? But don't be upset if it's taken me a little while to get back to you. That being said, I also, because I've got kids, I'm awake at strange times, and so sometimes I'm working at 2 o'clock in the morning, and so you might see emails coming out sometime between midnight and 2. So I do say my contact hours are by appointment. I don't mind if you're sort of a little bit lost in the subject, so you don't have a specific question but you don't quite get what's going on. I also don't mind setting aside half an hour to just spend some time to work through those ideas. Again, there's another caveat on top of that. I don't need to be your first point of call. We have 2 tutors available for the subject. One's been tutoring this subject for 3 years now, and he's my most senior PhD student, Jacob Rivera. Another one of my PhD students, but relatively new, Antonio Pizzulo. And it's quite common for a lecturer to have their PhD students as your tutors, largely because I'm teaching a subject that is important to me, so they're researching on the same stuff. They're good at their thermo. They're also good at answering questions, and sometimes they're a little bit less scary than asking a lecturer a question. Depends on whether they're grumpy or not, but usually these guys are pretty friendly. I would prefer that your chain of questions is, I've tried it myself, and I didn't get it, so I'm going to check with my tutor why I didn't get it, and if I don't understand their answer, I'll check with Rob. That being said, sometimes if you can't get hold of a tutor, just send me the same question, or CC me on the question so I know that the question's even being asked. But usually the tutors can sort you out. Particularly also on the admin of registration for workshops and all these other things, the tutors can also help you out. So Antonio will be running the thermo workshops. So here's the next thing. A couple of things actually. There's no tutes this week. Tutes start next week. Make sure you're registered for a tute, and please, as far as you can, try to go to that tute. If you miss your tute, on a one-by-one basis, it's okay if you go to some other tute because the content is all repeated. Try not to swamp any particular tute because then it just gets out of control. We have a non-teaching week in semester 1, which lines up with Easter. Easter this week is later in the semester, which is to say it's after the end of thermo. So we'll have a 6-week block in one session, and the Friday of the end of week 6 will be a mid-semester exam in class, and then you'll go into fluids in week 7 and then into Easter. There's 2 workshops. I've got the labelling wrong on this slide. I've realised as I've put it all together. In the registration timetable, workshop 1 is the fluids workshop, and you can tell because it's in building 176, which is not mechanical engineering, which is not my building. I'm in 170, and workshop 2 is the thermo lab. Let's see if I can get it up on the doc cam. Just to give you an indication, there's a bunch of workshops. You need to register in one. Now this, depending on how well this focuses, maybe it's easier without the light. It is easier without the light. So you can see the 6th to about the 10th of May is the fluids workshops, and then the following week down here, 13, 14, 15, 16 May is the thermo workshops. You need to register into workshop 1 and workshop 2. Make sure you're in them. If all the workshops are full, you contact Carol Barry, and she'll open up another workshop. So don't freak out if suddenly all the workshops are full. Now we've got plenty of workshops available to us, but we fill them up before we open up the next one. Okay? So that's now captured into the lecture capture if you want to go back to it, but also these things are available through your student portal for you to be able to register into these workshops. So you don't need to scribble that stuff down. It's just I wanted to let you know that these things exist, and it's one of your jobs as you're registering for this subject. Not only do you register for the tute, you register for the workshops. The workshops I will also refer to them as labs, because it's a couple of hours in a lab doing something. The thermo workshop is very fun from my point of view, because it's the world I come from, which is you get to play with an engine and work out how it works, check out its efficiency, or calculate a few things about it. The assessment for the thermo workshop happens in the workshop. So there's a quiz in the workshop, so there's not a report due in afterwards. The fluids workshop is a report that's due in afterwards, and it's due 2 weeks after you have your workshop. Oh. Get them back up. Okay. So on assessment, there's continuing assessment worth 50% of your total mark, and there's a final exam worth 50%. Final exams, 3 hours, hurdle exam, pretty similar to many of the subjects around us, with 50%, not 60, 70, 80%, because we want to do lots of stuff during the semester. What are your assessments? You've got a mid-sem, which covers thermo, because that's all we will have covered by the middle of semester. Because we've covered all of the thermo content, the mid-sem will have some proper questions in it. It won't just be, it'll have some relatively straightforward questions, and it'll have some deeper questions. And so we'll take a little bit of time beforehand to make sure we've covered the content. There's the 2 labs, they're worth 10% each, and then there's 2 assignments, a fluids assignment and a thermo assignment worth 10% each. I've told you when the labs are, I've told you when the mid-sem is. I'm not sure exactly when the fluids assignment will come out. Joe will have more clear info on that. Thermo assignment I want to get out to you at the start of week 4, and then you will have until after the end of thermo to get it in, which is to say week 8 happens after Easter. So you've actually got quite a bit of time to do the thermo assignment. It's supposed to take of order 10 hours of focused work. Now that 10 hours may be spread over a whole bunch of time. You may need to get some extra information from places. My thermo assignments tend not to be, here's the question on a platter exactly like we did it in class. Quite often it takes just a little bit of extra work on your part to hunt down the ideas and make sure you understood them. And there's always a component of explain something. So there's the maths part of the assignment, and then there's still maybe at least 10% of the assignment that tries to get you to think. Okay, so that's the assessment. We don't set mandatory textbooks because we don't want to make you spend hundreds and hundreds of dollars of something that's going to sit like a lump on your desk. But this may come as a shock. This is not a new subject. Thermo's been around for a while, and we're going to have a look at that. Which means that thermodynamic textbooks exist, and all of them are useful and helpful. Over the years, I grew up with Sengel and Bowles, which is the first one. In Melbourne Uni, mostly they used Borgnacki and Sontag. And then Moran Shapiro and Berner and Bailey is another one. It really, honestly, doesn't matter which edition. You can get any edition from the last 20 years. They've all got effectively the same content. The editors polish them up a little bit and tweak things around a little bit so that they can sell you new copies. These are available at the library or by whatever method you want to seek them out. I draw attention to this, quite a bit of the material. The structure of almost all thermodynamics textbooks follows a similar pattern. Here's the basic principles, here's starting to put them together, here's the analysis, and then here's the advanced subjects. And so if you're finding that you want to do more questions, deeper understanding, or if you need a different way of the same concept to be explained, and this is the useful bit. If you're stuck on something and you just don't get it from the way I've explained it or the way your tutor's explained it, other people have said the same thing in a different way. And that's one of the other places where the textbooks can become really useful. You don't need to read a textbook. You dip into them. So you go, I didn't get the thing you were talking about, entropy. Oh wait, entropy is 3 chapters. Okay, no, I didn't get the thing you said about entropy in a gas turbine. So you go to the gas turbine entropy bit and you read the 3 pages on it, and it may connect with you in a different way to whatever I've delivered. This is the bit where your study and learning is part your job. I can show you the information, I can guide you to what's good and bad information, I can guide you to how to think about the problems, but from now through the end of if you're all heading off to engineering degrees, you get more and more responsibility for your depth of understanding and for your ability to self-assess, did I get that? Did I understand the concept? So if you're sitting there going, I didn't get it, which means the lecturer didn't tell me well enough, that's not okay anymore. It's now time for you to go, I didn't get that, so I'm going to check with my friends, my tutors, my lecturer, textbooks, Khan Academy, whatever, until I get it. Okay, that's enough finger wagging from me. I've got a bunch of slides that I'd love to show you, but I don't want to just talk at you for an hour. One of the things I want to do is actually hear from you, and so I'm going to do that really annoying thing of get you guys to talk to each other. So what I'd like you to do is grab 2 or 3 people around you. I'm going to give you 3, 4, 5 minutes, and I want you to introduce yourself if you've not met before. And there's only 2 things I want to talk about. 1, what's something about the world that you want to change? 2, what do you think you're going to learn in thermo that might help you do that? They may be unconnected. Maybe the answer is nothing between the 2. But for the sake of the exercise, just try, just pretend. I'm more interested in the first question. What do you want to change about the world? You're not going to tell me, you're not going to stand up and all tell me that answer. The reason why I want you to get to talk to each other is because at the end, one of you will introduce someone else, tell me what they've done. So, chat. Find a few people around you, introduce yourself. If you're too far away to actually be able to talk to someone, move a bit. It's okay to move. If you're sitting up against a pillar, move over so you can chat to someone. change about the world? Let me know. Oh, that's cool. What did you guys want to change about the world? Anyone?
We all want to change our lives.
Okay. What are we going to learn? It doesn't matter. Anyone want to change anything else about the world? Or their friend? What did you hear? Anything interesting? Want to change the way that electricity is provided? Want to change the carbon footprint of the planet? Okay. Anyone else on that? No, you only got to spoke about save the world. Does anyone else want to save the world but through a different mechanism? Nice. Okay. Well, it can be damned, but provided I get the marks. What about you guys? What's going on? What is your friend?
This guy here wants to make the world more sustainable.
Sustainable. Okay, well, that's saving the world. I don't expect you to see a hand go up. And if someone else wanted to save the world, that's two. Or four, I guess. Did you guys want to save the world? Yeah. One. At least for a couple of years, at least until I graduate. Okay.
So this guy over here wants to change himself first.
Nice.
Himself.
Nice. Yeah. Don't change someone else until you heal yourself. I like that.
I like that one.
Okay. Yeah. So this may not happen if though, but I hope.
It's hard to change the world.
It is. It is. Okay. Well, that's a no. It's a good policy. What about up here? What did your friend want to change about the world? Design something. Okay. Have a lasting impact. All right. us a fortune on the way. Up here, what did you guys want to change that off? Renewable energy. Oh, there was more renewable energy. I was thinking there's more than one. Okay. Why?
Supposedly the energy is not enough.
The current amount of energy is not enough. Okay. Yep. Yeah. I don't mind which one. Did you have an interesting idea? Did he have an interesting idea?
Just want to become rich.
To become rich. This is what I like. This is not here. It used to be, if you were growing up in the 80s, that would have been the first answer that came out. They would have been you on the second level. I want to make money. And what about you guys? What do you want to change that about?
So something about changing the current combustion engines to more efficient design, so less emissions.
Making friends with the lecturer. I like that. Okay, good.
I mean, it's thermal.
It is thermal. It is. I mean, there may be a link. What did you want to do?
Self-driving cars.
Self-driving cars. Good, good, good. Okay, completely not thermo, but also still needs an engine somewhere. And was there anyone else who heard something interesting, some unexpected answer from their partner / friend / possibly lab buddy? Okay, so that's that first bit. Now I'm interested to know, do you think you're going to learn anything out of thermo? Does anyone have any idea what we might learn from thermo? What did your friend think we might learn?
We will learn many principles
Principles of what?
of thermodynamics.
Oh, well, face.
Yeah.
Okay. Principles of thermodynamics. I think that's fair. Okay. Good. We will. Okay. And what did this guy want to think we were going to learn about thermo?
About heat and engines.
Heat and engines. Okay. And we will. And what did he think we were going to learn about thermo? Because they said the word entropy before, which is a good catch. Well done. What's entropy? Good. You like at least 9 away. So it's pretty tricky. And what did she think we were going to learn about? Gas. Okay, good. Yeah, that's it. What kind of gas? Just gas. Okay. All right, fair. But we will learn things about gases and heat and pressure, engines. We'll learn things about moving this energy around. What did the friends think we were going to learn? Transfer of energy. Okay, what do you mean by transfer? All right, they're just phrases, so hopefully we'll learn these things. Okay. So that last bit is an interesting one. And they all, nicely, a lot of the stuff actually connects, which is why we have it in the subject. The thermo and dynamics, now if you've been flicking ahead in the notes, you'll pick up that they're actually Latin words that mean moving energy around. We're in this because energy is important. How to move energy around is important. So it's not just that you've got it, you need to use it somehow. That's really a big core of engineering. How do I get the energy from where it is to doing something that I wanted to do? Is a big part of mech-eng. Mech-eng may seem like it's about mechanisms. Those mechanisms are ways in which I can get the energy from where it was to where I needed it to be. If I'm moving something, that's energy and that's power. It's because I had a spinning wheel here and I wanted a pushing wheel here. It's because I had a lump of coal here and I wanted some electricity there. It's because I had a sun's ray hitting the ground and I somehow needed to get it all the way through to my car to drive the car. How am I going to do that? I need to understand how energy flows, moves, transfers, changes form. That's thermo. So thermo covers combustion and fire. Thermo covers engines. It covers refrigerators. It covers pushing and pulling energy around. And it basically covers almost all of the stuff that moves and happens and does. Importantly, and this is where it hooks back to the renewable energy thing, really importantly, one of the biggest things that thermo principles are used in is in the generation of electricity. And we're going to dig pretty deep into the cycles that are involved in that. And if you can get an understanding of where the efficiencies are and how one transfers energy all the way through to an output, you're a long way down the path of being able to work out how to construct the energy systems that are needed to let renewable energy work, to understand how the electricity that you've then produced, which is not an end use, it's a transfer medium, can then be used in a car if I know what I'm replacing, if I know what I'm changing. So we're going to really swim around in the core concepts, the fundamentals, I think was mentioned earlier on, the basic principles, until we've got just far enough that we can start to do some first round analysis. We're going to learn some new words and some new concepts. One of them is entropy. We're going to, later on, in a couple of weeks' time, we'll get into that. And we'll get into it deeper than just knowing that the word exists. There's a purpose to it and a mathematics to it that make it a useful tool. So let's have a look at that. This week, today, a little bit of the history of the topic and what it touches, what it influences. We're going to define systems, properties, and processes to the point where they then become useful tools for us. So a lot of what happens early on is us giving names and definitions to the things we're going to use. Week 2, we're going to have a look at gases. So again, if you've been flipping forward in the notes, you might see the word gas and you think I'm going to learn something about gases. We look about gases because in thermo, the motion of the energy is transferred by a something, and the something will be a working substance. Usually it's a working fluid, and usually that working fluid is a gas. Sometimes that working fluid is a liquid. Very rarely is the working substance a solid. So we're going to understand perfect gases, saturated, which is to say vapors, steam, gases. We're going to learn all about the wonderful world of property tables, which is how do I understand what's going on. Week 3, we'll write down the first law of thermodynamics and start using it. This is just energy conservation, so you will have seen it in physics already. Week 4, that's when we touch on entropy and work out why on earth we even need a concept like entropy, and then work out what we can do with it. Then week 5 and week 6 is where we pull all those ideas together and start using them properly for the first time to analyse something. So on the way, we're doing these little examples like a piston moves from here to here, a balloon inflates, boil this liquid, I've got a kettle. Week 5, week 6, we start to say I've got a car engine, I've got a refrigerator, I've got a steam, a coal-fired power station, I've got a big energy system, and now I want to know how efficient is it? How efficient could it be? What do I need to change? Where's the heat going in? How much energy did I need to run it? What was I getting out of it? You can do that by the end of this subject. So we refer to those as thermodynamic cycles, and I'll talk to you about why it's called a cycle later on. And as you map your way around the processes that go on inside these engines, you can then do these analyses. So we look at 2 different types of car engine. So the gasoline engine and the diesel engine, they have different processes. We look at refrigerators and heat pumps. We look at the steam cycle, which is what happens inside almost all of the electricity generation in the world. And so we put all of that together so we can understand quite a few really practical systems, really practical engineering systems. And then we have a test. So, some of these slides we've already talked about by voice, but I put them up so that they're in your notes, and these are also captured. In the LMS, I've broken up the subject into some modules, which kind of follow the weeks. And in each module tab, you'll have the lectures you'll have files called lecture and files called slides. The slides are whatever I'm putting up, obviously, on the screen, and the lectures are the written content behind that. So sometimes the lecture files will have the words more clearly written or in a way that you can understand better than just the pictures that are on the slides. So there's a reason why you've got 2 versions of each thing. So thermodynamics, heat and power, or heat and motion. The dynamics is power, but it's also movement. So we're interested in the science of heat and work and the properties of substance that connect to heat and work. The work part is the important bit. The heat part is the essential understanding of how did I transfer an energy from one form to another. So this is usually not immediately useful to me. This is useful. And so it's that journey.
I can't see that.
Good point. Good point. Right. So you couldn't see when I was talking about this. Excellent. Thank you. If that happens again, please let me know straight away. If it looks like I'm talking and waving to a board that's empty, I get on a groove. I talk quickly, and I do tend to enjoy talking about things. And so, yeah, anytime, just let me know. That was the week schedule that I said by voice. Now you've got it in your notes. It's also on LMS in the course outline. Thermodynamics, thermo and dynamis. This is as far as we got. I was just started rambling about heat and work and the properties of substances that connect to heat and work. The point of doing this stuff, anything that uses heat energy to do something is referred to as a heat engine. So this is car engines, jet engines, steam turbines as broad categories. If I go the other way, if I do work to make not heat, basically, or if I do work to move heat around, so a refrigerator is taking heat out of a place and throwing it somewhere else, that cycle can be analysed with the same principles, but back to front, and that's called a refrigerator, and we will look at those. And then the heat pump is a refrigerator, but instead of caring about the cold bit, I'm caring about the hot bit. So your air conditioner, when it's on heater mode in winter, is refrigerating the outside world and warming up the inside of your house. So we'll come back to all of those and analyse them in detail week 5, week 6. Why is this stuff hard? Why is it interesting? Why is it tricky? That's the kind of stuff that I worked on. This is a gas turbine engine with a quarter section cut out of it. A gas turbine engine needs to take air in, squeeze it down, put some fuel in, set fire to it, allow that to burn like crazy at 35 atmospheres of pressure, and then push past a whole bunch of fans that are called turbines, gas turbine, and that makes work, that spins the whole engine, which drives, these are the compressors, that drives the compressors, which were squeezing the air in the first place. There's the turbines down there. In all of that, the heat bit happens here. Here. I'm off by a few pixels. From here to here, in an annulus around the engine, is the squirt fuel in and set fire to it. Without that, the engine doesn't work. I need the energy from the fuel to push this thing. Once I've got it spinning, I can then, anything that's spinning, I can use to turn into work. So I find these beautiful. I find them quite remarkable. The first row of the turbine blades is operating 200 degrees above its melting point because of the magic of science. The combustors are this unbelievable optimization between efficiency and emissions and fuel use and power, and each of the things that you're trying to optimize for then forces you up against the limit of the other thing, and then you finish designing the combustor, and the turbine guys yell at you because you got it wrong, and the combustor guys yell at you because you got it wrong. So that whole system is an exercise in engineering optimization, and pushing it to be better is hard. It requires you doing your homework. It started somewhere else altogether. Turning heat into motion really started all the way back in the late 1700s. So James Watt, which is where we get the word watts from as a measure of power, was an industrialist and an experimentalist and a designer. He made this steam engine, and all this thing did, so the Smeaton engine, all the Smeaton engine did, so there's 2 engines up there, was if I boil some water, so I use heat, boil some water, the steam will push something, up it goes, down goes a lever. Magic. Compared to having to wait for the wind or the water, the wind to push a windmill or the water to push a water mill, it was. Because that means I could have that motion wherever I needed it. For example, in a mine, or for digging, or for pumping air, or for doing just about anything. The rubbish part was that I then had to wait until that chamber of steam cooled down again before the piston would come back. Just sit there going. Steam condensers, squeezes back down again, the piston comes down. So the big revolution of James Watt was to have a system where I could go whoop, and take the steam out and then start again. And so then I had a system of a lever that could pump up and down. That revolutionized mining, it revolutionized the mechanical industries, revolutionized this is the kicking off of the Industrial Revolution. The core to it was that I could put my transfer of energy into motion, energy into work, anywhere I needed it to be. The efficiency of these things was horrible. It was of order 1%. Of all the energy I dumped in, only 1% was useful work that came out. And yet it was still a fundamental transformation to the way the world functioned. You can be that bad and still transform the planet. And then the journey from there to where we are now has been quite remarkable. So that's where it kind of kicked off. We've got a couple of guys who were formulating the science. It's possible to do an experiment before you get the science. In fact, it happens a lot. A lot of the time the science is prompted by the why on earth did that happen kind of experiments. So the industrialist has worked out what he wants to do. Then this guy, French guy, Nicolas Léonard Sadi Carnot, was the first guy to really hammer out the science of this topic, of thermodynamics. The thing that he was passionate about, the thing that he wrote about, was about the idea that there was a best possible efficiency and then determining how close we are to that. So the best possible efficiency is not 100%. It's not achievable in the engines we're talking about, and we're going to go through that in detail. So the other big breakthrough, and it doesn't seem like a big breakthrough now when we're standing at the other end of 200 years of this, is that these transfers occurred through a working substance. Prior to that, so remember that we're at the cusp of turning magic into science in terms of world history. Prior to that, there wasn't an understanding of a connection between how heat moves, how substances change, and how work is done. They're unrelated ideas. And so if you can't connect them logically, if you have no physical framework for an idea that they are related, the idea that burning something could be turned into motion doesn't exist. So to lock that down as a body of science and start proving it is a scientific breakthrough, and because it allows you to then start making predictions and then test it, it allows you to pinpoint where are the inefficiencies, because now you have a mathematical framework for doing the analysis. And then he worked out this idea of a cycle. Given that a lot of the stuff starts from cold air and gets back to being cold air again, or cold water going back to being cold water, you can then analyze it in a loop, and that simplifies quite a bit of maths. So Carnot will come across around about week 4, Carnot's cycle, ultimate efficiencies, best possible efficiencies of any particular thing. He wanted to know the maximum work you get out of any given unit of heat, and that's a very engineering goal. There are other famous people. I just like showing photos of men with beards. There's Joule, who was a beer brewer, but he also showed that mechanical energy could be converted to heat, which is the opposite of Carnot. Carnot was saying heat into mechanical energy, but Joule was able to show that mechanical energy could be turned into heat. Now, you don't need to do much more than that to be able to show that, but he did it mathematically and in a scientific framework. And people didn't like that. It was really upsetting the worldview of how these things are, whether these things are even connected. Lord Kelvin, which is William Thomson Kelvin, again, a name you might be familiar with. This guy did the homework to define that absolute zero existed long before the experiment could be done to prove that that was basically bang on. And that's a pretty impressive feat, because up until that point there's no particular reason to think that there is a maximum or a minimum temperature. And it comes from an understanding of thermodynamics. In here we've got Clausius. Clausius is not necessarily a dinner table name, but he introduced and codified the first and second laws of thermodynamics, which we'll get into. And then Gibbs. Gibbs, again, you would generally haven't come across until you've done combustion science, so this is advanced thermo, but he worked out the statistical foundations of thermodynamics, which is different to, we're going to do it at the mechanical level, at the worldview level. He did it at the atoms shaking around level. So why do I care? Now, this stuff I have this in my lecture notes because I like to use it in discussion. However, I decided that the discussion we did earlier was more interesting. So this is in my lecture notes to prompt you to think literally everything that's going on around you has been influenced by this world. Anything that required energy to make happen, or the transport of you to get here, or the transport of stuff to you, the refrigeration of your food so that you're not dying, the fact that your phone functions, the lights are on so we can study in a room that should be dark. All of this has come from, I mean, I don't want to claim that thermodynamics runs the world, but we're not far off. And so the mech-eng world that Thermo lives in is a core part of the devices that enable these technologies. So a couple of ideas. You don't get tourism without this stuff because you can't move people in a plane around the world until your gas turbine works. You can't gas turbine won't work until you get the efficiencies right. You don't get to drink milk until you can have it cold enough. You don't get vaccinations or medicine until you can refrigerate it. You don't get trains, so you don't get goods from the other side of the world. You don't get mangoes from wherever mangoes are growing, potatoes from wherever potatoes are growing. At the same dinner table, you only get the thing that you grew right next to you until you can move stuff around, until you can turn heat into work or vice versa. Why now? Why on earth would I care about this stuff now? The thing that came up from our conversation, one of the main topics that came up was Save the Planet, Sustainability, Renewable Energy. This is Australia's greenhouse gas inventory, and we're talking megatons of CO2. In that list, 70% of what is emitted is coming from processes that could be benefited by an understanding of thermodynamics. That's the bit that keeps me going. So it's not to say that thermodynamics is responsible for 70% of greenhouse gas emissions and therefore we shouldn't have thermo. Saying the stuff that goes on in our world, over 90% of transport is run off fossil fuels through a combustion engine that a study of thermodynamics could improve the efficiency of or change the fuel it runs on. And 90% of our, 85% of our electricity is still being produced by processes. Well, even if you replace the source of heat, if you're burning biomass, biofuels, you still need an understanding of thermo. And many of the solar cycles that transfer solar heat into electricity run on thermodynamic heat pump cycles, heat engine cycles. These problems, the climate change problems, I don't need to tell you this is stuff in your living. Far greater threat to the world than international terrorism. UK chief scientist, the most severe problem we're facing today. Now, the interesting thing is this is stuff that needs to get fixed, and it needs to get fixed in about 30 or 40 years, and interestingly, that's basically your career. Now, some of you are going to go make money somewhere, some of you are going to go design a new invention. Many of you will become engineers, many of you will be involved in fixing these problems somehow in your lifetime. I get the luxury of just teaching you the beginning footsteps, how to think about the world. I'd really, really appreciate it. My kids would love it as well if you did that. So, best of luck. So there we go. I've left myself about 30 seconds to do a little flash forward. I've spoken twice now, a couple of times actually, about laws, thermodynamic laws. And so rather than leave it until week 3, week 4 to start to see these things, the first law is nothing more than energy is conserved. If I have a system, I put energy in. If it comes out, there's been no change. If it doesn't come out, there's been a change. So whatever didn't come out stays in. It's not magic. If you've ever tried to diet, you probably worked that out. If I haven't been exercising and I put food into me, I have a change in my internal energy. The second law is the entropy one. The second law, the point of it is that whatever I put in, I can't even get all of it out again. And that's the core of it. It also tells me the mathematics of how to work out the best that something can be. There is a zeroth law and a third law. We don't spend a lot of time on them. The zeroth tells me that if something is a certain temperature and it's the same temperature as something else, then they're at the same temperature. It might not seem like a very important law, but it makes a difference once it's mathematically valid. And the third law is that there is an absolute zero. I also have a page up there we spend a lot of time on steam, particularly steam. So we talk about vapor cycles, we talk about fluids that then can boil, and they are a mix of boiled fluid and the liquid fluid. But we spend almost all of our time on that concept, on the idea of steam, because water is bizarre. It's a really, really normal thing for us to live with. Its properties are unlike any other chemical that you'll come across, and they're utterly necessary to the way our environment functions. One of the biggest things, if you've ever had an ice cube in your drink or seen an iceberg, the solid is floating. That's weird. The idea that the solid could be less dense than the liquid is weird. The amount of heat it takes to boil and freeze is huge. Its surface tension is high, which means it can fall like droplets. It's a solvent, which means it can wash ions out of the air. It can be used as a transport mechanism for chemical processes around the planet. It is a very, very weird molecule. And one of the things we do is map its properties out on a table because of how hard it is to write the equation for how it works. And so we just say, enough, the equation's too hard, let's just write it down. All right, so that's the Welcome to Thermodynamics. Thanks very much for coming in. I'll see you tomorrow at 9 o'clock and then on Fridays at 3:15. We're always in the same room, so you get familiar with here and the cafe and the walk down and be able to watch the construction over the next 3 months. Thanks for coming in.